What's up, everyone? This is going to be the first video of a few videos covering heat transfer. Um, this is this won't be super detailed. You'll definitely get more out of your heat transfer classes in university, but hopefully this will help you understand it a little bit more. In the next video, we'll cover more of the equations and applications and go over some practice problems. But for now, I just want everyone to get familiar with what we mean by heat transfer. So yeah, this is heat transfer 101. What is heat transfer? So heat transfer is the process of transporting thermal energy, and it's always driven by a temperature gradient. So whenever you have something hot and whenever you have something cold, energy is being transported between them, and that energy, the thing that we call thermal energy, that's different than heat transfer. Thermal energy is an energy that's associated with an object because that object has random movement in its atoms. So, you know, these guys are vibrating, these little atoms are vibrating, and because they're vibrating, they have a certain kinetic energy. And now that average kinetic energy, or that mean motion of those molecules, is associated with what we call temperature. So that's what thermal energy is. And if you've ever heard of the Kelvin scale for temperature, where it goes 0K up to whatever K, usually. And you've heard Celsius is 273K, right? So 0 Celsius, 273K. Um, that 0 Kelvin, that is associated with absolute zero. So that is absolute zero, and absolute zero basically means that these guys, they're really frozen. You know, they're frozen in place. Um, so that's kind of how that scale is derived. 0 Kelvin is associated with atoms that are frozen. Um, so yeah, okay. So what is heat transfer in engineering? Where is it found in the world? Um, how do we use it? So it's found everywhere. In any engineering application, most engineering majors have to take a heat transfer course. It's found literally everywhere, and if you start looking for it, you will find it. Think of anything that's hot or cold, and heat transfer is associated with the engineering design of that product. So let's specifically take a look at some rockets, rocket examples. Um, on a propulsion fluid system standpoint, we care a lot about, the nozzle of the rocket. So I put this SpaceX Raptor, um, SpaceX Raptor hot fire here. Um, this thing gets hot, really hot. And how do they cool it? How do they figure out how hot it gets and what they need to do to cool it? They use heat transfer. So we can get more into that specific heat transfer analysis. That's something that I've got some experience with, but we'll get into that later. So rocket engines get hot, and then at the same time, rocket engines are fed by cryogenic propellants that are really cold. Um, so we have two kind of opposite spectrums. We have to deal with stuff that gets really hot. We have to deal with stuff that gets really cold. And there's different considerations for both. But at at the fundamental level, heat transfer is used to analyze both applications. So also just as an aside, this word cryo, um, what I really mean by cryo is I don't just mean really cold. It's used for things that are gas at room temp. um, and they become, then you chill them down until they're liquid. And that's usually associated with a really cold temperature. For reference, liquid oxygen, oop, I misspelled that, a really cold temp. So for reference, liquid oxygen, LOX, um, that's around 90 Kelvin that we see it at. But I mean, that's on PSP's rocket. That's at 335 psi about. But anyway, really, really cold. Usually we're talking about like negative 300 Fahrenheit. I think that's a little bit more relatable. Okay, so we get hot things, we get cold things. That's kind of what we're doing on the rocket. Okay, so there's three modes of heat transfer. There's conduction, convection, and radiation. I'm sure you've all heard all three of these words used in some capacity. Conduction's used a lot in electrical applications for connectivity, um, and there's actually a very interesting corollary between electrical systems and thermal systems, as well as fluid systems. And we'll get into that a lot in the next lecture. Convection, I mean, everyone's baked, right? Convection oven. Um, Radiation, I'm sure you've heard radiation in terms of like nuclear radiation, or maybe you've got some exposure to the subject and you've heard of sun and fire as sources of heat radiation. Um, yeah. So conduction is, I would say, I would say that think of these as, I think of these as levels. I mean, these are all hard modes to analyze in and of themselves, but I think the easiest one, and everyone starts out with conduction, then you kind of move on to convection, and convection can get really, really crazy. And then you move on to radiation because radiation is, it's just so much different than conduction and convection, and it gets really complicated real quick. But don't worry, it won't be too complicated after I explain it, hopefully. Okay, so conduction is heat transfer in a solid or still fluid. Um, this is mainly a diffusion process. So it's got the same exact equations with different coefficients as a mass diffusion process. So if you've done a chem lab and you've seen a drop of dye in water and the way it spreads through the water, it's diffusing. Conduction is very similar to that. Convection is a special case of conduction. You've got heat transfer at an interface of a solid and moving fluid. And that fluid kind of picks up the heat from that solid or distributes that heat to that solid, proportional to how fast it's moving. The best way I can explain it is your body is at something like 98, 97 something degrees Fahrenheit. You're you stand in wind that's slightly cooler. Think about how cold you would get with like no wind versus a slow wind versus a very strong breeze, versus a really really fast moving airflow. Um, you know, Obviously, if there's no wind, you're going to be baking. You're going to be hot. If there's some wind, you'll cool off a little bit, and if there's too much wind, you'll be cold. So that's convection at play. You're convecting, the wind is convecting the heat away from you. And now radiation is is a different ball game, and that's the transfer of heat through electromagnetic waves. And this is the only thing that can occur through a vacuum. These two, they need a medium to act through. Um, Radiation is not. not beholden to any particular medium. It can occur through a vacuum, and that's how the sun transmits its thermal energy to us by way of radiation. We've got all those millions of miles of vacuum in between us and the sun, and we still feel its heat, and that is because of radiation. And we'll get more into radiation later on, but yeah, so these are three modes of heat transfer. So when we look at something that we want to analyze or something that's being heated or cooled, we're gonna categorize that problem into either conduction, convection, or radiation, or a combination of all three. And and the reason we categorize these in different ways is just for, it's good bookkeeping, and it also helps us understand physically where that energy is going. Okay, so let's take a little bit of a closer look at some special properties of conduction versus convection versus radiation. So here, I just made this little gradient here because conduction is a gradual change in temperature through a still medium. So it's you can see that this color is being diffused, and it's a very slight diffusion, and that's usually how conduction spreads. Convection, on the other hand, you'll almost always have a sharper temperature gradient here. The if you have a hot surface here, so this is a hot surface, and a cold fluid here, what ends up happening is if you follow the temperature going this way, you're going to find that the gradient changes very rapidly. Um, Going from the surface into this medium here, from this surface into the cold fluid, a very sharp change in temperature. Um, and radiation is you have two objects at different temperatures, but there's a space in between them. And so the only uh, heat transfer that's occurring between them is radiation. Obviously, it's not the case if, like, you've got two a very hot object like a centimeter away from a cold object. That would heat up the air in between them, and there'd be a little bit of conduction and convection as well. But what I'm talking about is something like the sun and the earth. Okay, so finally, I'm going to end each lecture hopefully with a table that has some of the terms that you have to be familiar with. So, in the grand scheme of heat transfer, these are some of the terms that I picked out that you should be familiar with. And that's thermal energy, which is what we talked about. Um, that term usually gets a U. Um, you can also see it as a small u. Um, as a hint, most of the time when you're talking about like something like small u or anything that is lowercase, that usually means that it's a specific property. So if you see lowercase u, that means it's a specific energy, and specific means usually mass specific. So um, it would have the units of joules per kilogram. But anyway, you'll learn more about that when you take your thermo classes. But yeah, so that's thermal energy, the random vibration of matter. You also have temperature, which pretty straightforward unit, Ali symbol. Um, and it's the way that we measure a thermal energy that's associated with an object. That's how hot it is. And these are the SI units only, but which is what we will use. You'll see that either as Kelvin or Celsius. You can also see that as Fahrenheit or Rankine. Okay, so heat transfer. heat transfer is usually a symbol of Q. It's the amount of heat transferred. Um, yeah, that's we'll get into that a little later, but what we care mostly about are these three right here. These have to do with all the equations that we're going to be using. The rate of heat transfer is the thermal energy transfer per unit time. So this is kind of like the derivative of this guy right here. Um, if you take the derivative of that with respect to time, you will get the rate of heat transfer, and that is in watts, which is also known as joules per second. Um, then we also have heat flux. So this term here confuses people. Flux is kind of any sort of uh, like transport of something through something else. So usually we'll call it an area. So per area. So you'll see if you're looking at like a wall, this has got some area associated with it, and heat flux would be the heat transfer through that area. So it's always in a unit of per area, so per meter squared. Um, you can also have volumetric flux and other kinds of flux, but all we're saying is if you're looking at the energy transport path and you put a cross section, uh, what's the cross section is traveling through? Is it a cross-sectional area, a cross-sectional volume? That's what we mean by flux. Okay. Uh, Another thing to look at is the heat generation rate. So what do we mean by that? What we mean is heat generation is when you have an object, there can be heat transferred into it or out of it, but sometimes it can be making its own heat. What we mean by that is maybe you're looking at a chemical reaction, and that chemical reaction is generating heat while reacting, and then that heat's being taken somewhere else. So, or if you were to consider something like an oven or a stove inside of another control volume, like a reference volume, we'd consider that kind of, it's generating heat. The stove is generating heat. It's got a heat generation rate. So, and I apologize if I'm using some language that isn't friendly to the uninitiated, I guess. Please let me know if you need more things explained. This is my first time doing something like this, so yeah. Okay, so heat generation rate, and then there's one more thing I wanted to talk about was this guy right here. I don't know how many of you have taken calculus. For the ones who have taken calculus, you will be best reminded to not confuse this with uh, derivatives. So in calculus, this apostrophe. So if you have something like x prime here, that means dx dt, or some sort of derivative, right? What we mean in heat transfer, though, we don't mean a derivative. What we mean is it's per unit some dimension. So q prime relates to unit length. So when you see q prime, that means it's heat transfer per unit length. Um, q double prime means per unit area, in which case we call it heat flux, right? Unit area. And then you'll also see triple prime, and that is per unit volume. And that's particularly important when you're looking at 3D analysis. So again, this prime, don't be confused. This does not mean a derivative. It is a per unit dimension. Okay, great. Um, that's all I wanted to cover with Phi's set of slides. Super quick overview of heat transfer. I'm sorry if that ran a little long, but yeah. Next, we will be getting into steady state conduction in the next video. So please watch this video, follow along, and um, please let me know if you have any feedback, suggestions, comments, questions. I will try my best to answer all of them. Thank you.